Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my great pleasure to introduce Oleg Komogochev. Okay. It's hard for me to pronounce Russian name. Yeah. I know Oleg from his work and met in person early this year at HR 2014 in Florida. Why is my voice just suddenly dropped? It's okay? Yeah. So Oleg is an associate professor at the University of Texas State University. He has done a lot of work in eye gaze tracking, but as well as a lot of applications like in privacy, security, human-computer interaction. And today he will talk about some of the projects he has been working on.
Thank you so much for your introduction. So today, primarily, I'm going to talk about eye movements in biometrics and human-computer interaction. Each scientist, each of us, has a motivation. So my technological motivation can be presented with this short video. Oops. Getting the cursor is tricky. There we go.
A road diverges in the desert. Lexus. The road you're on, John Anderton, is the one less traveled. Make sure you all undive.
Good evening. You can do the old-fashioned John Anderton. 21 stands provides gourmet cuisine. John Anderton. You can use a Guinness right about now. Stressed out, John Anderton.
Escape from it all, Harrison. Get away, John Anderton. Forget your troubles. It's slow, John Anderton.
Well, if you looked at this video, you are able to see two things. First of all, the surrounding environment is able to detect who the user is from a distance, whether it does it via eye movements or iris tracking, that's another question. And the second, that he can interact with the environment by moving the eyes, and basically wherever he looks at, the environment detects where he's looking at and presents the content that is personified to that person. And in my lab, we are tackling both problems, and so today my talk will include the discussion on both. Well, let's start with why biometrics exist. Every day we use quite a lot of passwords. As a humans, it's very hard to remember the amount of passwords that we need to use. And though we have to use tens of passwords, usually people use 3, right? The most secure one, then the medium, and then the one for the junk stuff. Well, biometrics is a science that targets to identify a person based on who the person is, rather than what the person remembers, such as password, or what the person has, such as some sort of ID card. However, the biggest challenge in biometrics is spoofing. And I would like to present a short video that would talk about spoofing. So you can see here that the intruders took a picture of authentic user's eye, imprinted it on contact lens, and then now they are trying to fool very sophisticated biometric system to get access to some goods. And you can see that they were successfully able to do that, right? And so with my work, we are trying to prevent this. And we are doing it by identifying a person based on eye movements. And for you to understand this technology, it's very important to consciously experience those eye movement types. And so today we will together experience them, the majority of them. So the first eye movement that I would like you to experience called eye fixation. Could you please look at number 1? And now once you're looking at number 1, your brain is getting high quality information when you're looking at this dot, and this is how we basically perceive the world around us. The second eye movement that I would like you to experience is called the saccade. So could you please look at number 1, and now look at number 2. Saccades are extremely rapid rotation of your eye. The velocity during saccade reaches degrees of 700 degrees per second, and that's why we are not able to see during saccades. So let's see if there was hairy monkey running between those two dots. When you were moving your eyes, you would not able to see the monkey. And we see the world around us by having those fixation spots and moving between saccades. And actually, we get the illusion of the stable picture with all information around us from our brain, but it's a false sort of image because the brain reconstructs all this information from those little fixation spots that we exhibit. And actually, the acuity of vision during a fixation is quite small. So if I extend my thumb, just the width of my thumb I can see with high quality, and everything else is blurred. And so if it was the other way around, so let's say we could see everything with uniform quality around us, then the cell distribution in the eye would be different, and our brain would basically burn out because it would have to analyze all that information. And the final eye movement I would like you to experience is called smooth pursuit. This is basically you see when you are driving a car. And depending on how well you can track your target, the quality of your vision will change. This is an example of a signal that is recorded from an eye tracker. An eye tracker is web camera-like device. So this is the example of one of those devices. Right now, it's very cheap, costs just $100. And the signal that you get is similar to what you see on the screen. And here, in the bottom, you see the time. Here, the position, the horizontal position. And you see those fixations and saccades. And you can see that fixations are quite jittery. Saccades are quite rapid. And this is the signal that you have to work with to basically analyze who is who. So right now I will talk about how it is possible to identify a person based on those eye movements. Well, in the approach that we decided to take, we are not just slapping some machine learning algorithms on the raw positional data that we are recording. One of the aims is really understand what is happening with human, and more specifically with physiology of the brain and physiology of the eye, to identify a person based on those characteristics. In case of eye movements, there are two main components that make eye movements possible. This is the brain, and the brain sends a neuronal control signal to what is called a oculomotor plant. And a oculomotor plant is basically the eye globe and the muscles that rotate the eye globe. And the ideas that I would express today would allow to identify a person based on the structure of the oculomotor plant and based on the functionality of the brain. Also, what is important to understand that brain encodes two important questions when working with eye movements. Where the eye is going to go next, and to less extent, how the eye is going to go between 2 points. And the oculomotor plant encodes the information how the eye is going to go from one point to the next. And by decoding this information, we will be able to identify who is who. Well, this is the example of two people reading the text. One person is identified by the red dot, and another person identified by a blue dot. If you look at this video carefully, and I hope you can see it, you really can see that spatially and temporally, those two people move their eyes differently. So this is sort of an intuitive way to explain that there is difference between people in terms of how they move the eye. And this is two overlaid scan paths. Scan path is basically sequence of fixation and saccades. And you can see here that indeed the movements are different. A little bit more information. I will start by identifying a person based on oculomotor plant. So oculomotor plant is the eye globe and the muscles that rotate the eye globe. If you look at the autonomy, there are 3 pairs of muscles. 2 of them are responsible for rotating the eye globe horizontally. 2 of them are responsible for rotating the eye globe vertically. And 2 are responsible for the torsional rotation. And again, my goal here is to identify a person based on the properties of those muscles and the eye globe. And this is the moment in time where you look at me, the presenter, not the screen. In my hands, I have a human muscle. If the muscle is not innervated by the brain, it acts as a rubber band. Basically, you extend the muscle, it pulls back. So it has passive elasticity. The picture becomes interesting when, for example, we decide to make a saccade, and then the brain sends the neuronal control signal to the muscle. It sounds like this: bum 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 bum, bum 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 bum, bum 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 bum. So this bum 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 is a very rapid increase in neural finding to contract your muscles. And when the muscle is bombarded by neurons, it has very interesting characteristics. For example, the amount of force that the muscle is able to generate is different depending on how far the muscle is extended or contracted. Why does it happen? Because in the muscle we have filaments. Those filaments, well, can be represented roughly like this. And so when the muscle is shortened, the signal cannot penetrate the middle fibers. And that's why the amount of force is less than possible maximum. And when the muscle is extended, the overlap between fibers becomes less. And again, that's why the maximum amount of force is less than the maximum. Another interesting property that the amount of force changes on how fast the muscle is contracting or expanding. And this has to do with the chemical reactions that take place to basically change the neuronal control signal to actual contraction. Also, the fibers of the muscle are connected by tendons. They're connected by tendons to the eye wall and to the eye globe, and also fibers between themselves also connected by tendons. So tendons also expand and contract, and we can create some elements that would model them. Okay, now you'll probably be happy to look back at the slides, not me. In addition, we have such things as eye globe inertia and some viscous properties such as fatty tissues around the eye. Well, what I'm going to say next is that now I would like to model the eye globe, the oculomotor plant, mathematically. And so I'm going to put the elements that have one-to-one correspondence between the actual anatomical elements in the eye and the components of the model. And so the first component is that neuronal control signal that I try to mimic by bumping. And the second part is the active contractile force that is generated by this neuronal control signal. Here I have a linear spring that basically is responsible for these filaments that are connected to each other, for this length tension part. And I have component that is responsible for the tendons. And by the way, this is a system in equilibrium. The eye is stable. It's bombarded to make the eye staring straight ahead, but it's not moving. So as I mentioned, things become more interesting when the muscle actually starts contracting. In this case, we have a damping component that is added to the system, which is responsible for representation of this force-velocity relationship. Additional interesting things that I hope you can see that, for example, when muscle is contracting, that the length tension part of the component shortens. Well, you can imagine it like this. And the series elastic, the tendons, become longer. And so this is all incorporated in the model. And right now, we'll just give you a few ideas. I'm not going to go into the deep math. I understand this is a Friday afternoon, and the weather is pretty nice here. So what I'm going to do is basically just build the model by creating mathematical equations for each muscle that is involved in rotating the eye globe. Actually, there are two types of muscles, the agonist and antagonist. Agonist that contracts and pulls the eye globe, and antagonist, the one that is being pulled and expands. And so what I'm doing here is basically building differential equations that would represent the system. And this is the one-dimensional representation that is responsible for describing how the horizontal component of movement is formed. And so basically, for each muscle, I would have a differential equation that would describe how the muscle works. Then I generate the third differential equations by employing a Newton's second law that says that all forces combined that are acting on the rigid body equal to the mass multiplied by acceleration. And in my case, I have inertia. So, and what I'm doing, I'm basically summing up all of those forces. Additional interesting idea is that when the neuronal control signal is created by the brain, it looks like a pulse step function. Remember that rapid increase in firing? Bam, 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 bam. So this is what this graph represents, just a rapid increase in firing in those neurons that send the control signal to the muscle. Well, if the active force inside of the muscle would change in the same rapid way, the muscle would just tear apart. And so that's why, because of those chemical reactions, it's basically smooth, and we have a low-pass filtering process to represent what is happening. And again, for each of the muscles, I have a differential equation that describes that. As the result, I have a two-dimensional model of a oculomotor plant that has 12 differential equations, 36 different characteristics that have a correspondence between the anatomical properties and the components of the model. And what the model is able to do is it is able to accurately simulate saccades. And this is the result of one of the simulations. The gray area is the simulated signal, and the black line is the recorded saccade. And you can see that they differ, but you should believe me, in the world of eye tracking, that's not bad. Okay, so again, coming sort of back to biometrics. When I started working in this area, the idea that I had in my head is that all those anatomical properties, what if those anatomical properties are really different from person to person? Before, nobody tested this hypothesis. And then the question that you should ask me, well, how did you get those initial parameters with which you simulated those saccades? Before answering this question, I would like to remind you again a little bit about spoofing, right? So we are trying to combat that problem of spoofing. And so here, additional little video. Actually, the system behaved quite well, right? These were John Anderson's eyes, and he identified as him, but unfortunately the eyes were removed, right? So again, in the design of the system that would use whatever method, we really would like to make sure that nobody would remove any part of the body to be admitted to the system. And actually, removal of body parts is not a joke. I think a very rich businessman in Kuala Lumpur was dragged out of the bar, and the thieves basically put his finger on his expensive Mercedes so they can drive. But unfortunately, the system required continuous authentication, and then bad thing happened to him. But of course, he was alive, but without a finger. And so that thing is really important to prevent in biometric system. Okay, so remember those ideas. So I have a oculomotor plant, and why I showed the video is that if the eye is basically removed, right, then the system is not live, right? So it's impossible to extract those parameters from the eye movement signal and identify a person. So if this is the actual method of identification of an individual. Nobody would even think removing your eye and trying to, present it to the camera. Anyway, so those parameters, initial parameters from the model, were extracted in this way. So if you are sensitive to blood, I would like you to ask to close your eyes for the next 15 seconds. So what is happening here is during the surgery, the surgeon cuts the eye, and he uses a special instrument to take extraocular muscle out, which is connected to the force measuring device, which basically is able to tell us how much force is generated at different eccentricity levels where the eye is looking. And so those initial parameters were collected as a result of surgery from 3 people and were averaged in the month. So,
how do you find a volunteer for that?
Sorry?
How do you find a volunteer for that?
A video?
There's a volunteer.
A volunteer. Oh, no. They're getting their eyes corrected. This is a strabismus surgery. So it's actually part of. So it's actually doing good, though it looks very painful. At the end, the person gets a corrected problem. Okay, so the approach that we have created doesn't harm anybody. And you have this little baby who is looking at eye tracker. Again, if you look at the eye tracker, this is nothing else than basically a web camera, right? So it has 2 image sensors and then some infrared lights. And another interesting idea that in terms of hardware, it's extremely similar to iris recognition device, that basically they are identical. And so this is something that I would like you to have in mind until a certain point in the presentation. Actually, not very many. And this is something, again, that I will mention later as a possible future applications. So this is the algorithm that we employ to extract those characteristics and to identify a person. So we record the eye movements by an eye tracker. Then from the repositional signal, we extract those fixation and saccades that you saw colored previously. And then we have the mathematical model of a oculomotor plan that I presented to you. And the idea of the model is to simulate exactly the same saccades that were recorded. Well, we start with the average values, but they don't match well in terms of what was recorded. So we have an optimization algorithm that basically allows us to select better parameters that provide a much closer match. And we go through this multi-iterative process with goal of reducing the error between the classified and simulated signal. And when this error is the smallest, then this vector for each saccade goes to the biometric template, and then a person can be identified based on this template. Can you guess who are those 2 people? One of them is important in image recognition world, another in biometrics world.
Is Lisa Doglin?
No. It's Kevin Boyer and Lena. Okay, so this is another look at how the template is generated. Remember those fixation and saccades. So for each saccade, we are getting this vector of parameters, those anatomical characteristics of the oculomotor plant. And then this template can be matched to another template. We employ Hotelling T-square test that proved to be the simplest, the quickest, and the most accurate. So I'm going to present actually with the result of this method. The system that we investigated the performance of this method had a very accurate eye tracker. So this is a commercial grade system, very expensive and very accurate. The data capturing conditions are ideal. So for example, we are sampling at the rate of 1000 hertz. Our calibration accuracy is on par with physiological capabilities of the system and the eye, 0.5 degrees. Once again, this is the quarter of my thumb. This is a tower-mounted system that also adds accuracy. And this is the largest study so far in terms of the number of subjects. So we have 335.
How much time did you ask the user to look around?
100 dots. So this is actually the next information that I was going to present. So here we have a dot of light that is jumping back and forth. So the idea is to execute large saccades, so approximately 30 degrees. So I would say, in front of me, this would be this much. So the person has to make 100 saccades. And so our biometric template consists of 100 vectors.
To the same 2 points? Or
Same 2 points. Same 2 points.
Unpredictability, it's...
I would like to come back to the question unpredictability when I talk about spoofing. But this is a great question. So for those of you who may be not familiar with the world of biometrics, there are several metrics that basically identify how accurate the system works. So first of them is false acceptance rate, and basically this is the percentage of the attempts from the imposters that are accepted as authentic users. False rejection rate, and those are attempts from the authentic users that are erroneously rejected. And what I'm going to present to you, because I have a lot of data, just equal error rate. So those are two, this is the point where false rejection rate equals false acceptance rate. And this is a point that is achieved just by varying the threshold that distinguishes between two templates. And basically, in identification scenarios, basically the metric called IR, and this is what is the percentage of correctly identified individual there was. So this is the graph, and what the graph represents is basically number of subjects. So we started with 50 and then proceeded increasing the number of subjects to 335. And basically what it tells you how good the system scales on the big scale. So EAR is really representation of the performance of the system in authentication scenario. Basically, when you come to the computer and saying, I'm Oleg, and the system says yes or no. So with this, the EAR was approximately 14%. And just for the sake of thought, the EAR for such system as fingerprint is 2%. And for the iris, it's even better. Depending on how good is your data, you can get it to 0.1 or even lower. And you can see here that in terms of authentication, the performance is flat. And possibly for authentication, we even don't have to increase the number of subjects because we know already so much about the distributions of imposters and authentic users. But you can see that identification rate really goes down. And so what we can see right now that the system can be used, for example, in the authentication mode, but not in the identification mode. And by the way, just for the reference, FBI considers, from what I've heard, FBI considers acceptable performance of face recognition system at EAR of 10%. So very close to the 10%. But again, it's also important to realize that this is an ideal scenario of data capture. So remember, we are talking about two physiological traits. So one of them is oculomotor plant, and we call it for short OPC characteristics that allow to identify a person, and the second one is brain. So right now I just described this part, and now I'm going to talk about the brain. Okay, there are multiple zones in the brain that are responsible for vision. Almost all of them have very complex names, and I don't want you to get lost in them. So our goal is to identify the physiology of the brain and how it works based on eye movements. But we started with processing simple metrics. And those simple metrics that represent brain behavior are, for example, number of fixations and duration of those fixations. Also, we can analyze saccade amplitudes because they are created as a result of the neuronal control signal. Also, such thing as saccade waveform. For example, here you can see this is the velocity of the saccade, and you can see here there is an acceleration period and deceleration period. So how those characteristics are related to each other in a human also can tell who is who. There are also some fundamental properties of the human visual system. So there is what is called amplitude relationship. This is how far you go with your eye and how long it takes you to go with your eye. And you can see that some fundamental work says this is a linear relationship, others says this is exponential, but basically you can see that there is a lot of variability in the data, and we have a certain fit. So this fit also changes depending who is who. Another fundamental characteristic is what is called main sequence relationship. This is a dependency in terms of how far you go with your saccade, the amplitude, and what is your peak velocity during a saccade. And this is exponential relationship, but again, you can see how much variability we have in our data. And for example, those crosses represent a certain eye pathology that you can immediately see by looking at this relationship. And again, different people have slightly different relationships like this. Also, we look at the metrics that are related to the scan paths. For example, here you have 4 fixation dots, 1, 2, 3, 4. And then the person basically makes saccades between those points, and those are fixations. So we looked at the length of the scan path and inflections. And inflections is how frequently the person changes the gaze, the direction. Also, we look at the area. How large is the area that is formed by fixations? And also the distances between different fixation groups. There are quite a few statistical tests that allow us to compare biometric templates, because the biometric templates that you get from the brain-related stuff are, first of all, multidimensional and have different lengths. So there are different statistical tests that allow to exploit certain properties of the data. For us, we determined the Kramer von Mises test worked the best to compare individual distributions. And because you have multiple distributions on which you have to make decisions, multiple distributions of this eye movement data, you also can use information fusion techniques to improve the performance. And the one that worked for us the best was random forest. So this is a performance of the method. And again, this is the number of subjects that we are employing, and this is equal error rate and identification rate. So identification rate is this dotted line, and equal error rate is this line. So this brain-related metrics, as I call them, provided us with the best authentication performance. So this golden line of 10%. And what I told here by some people who are very good at biometrics is that probably here was some statistical noise. But again, you can see that for small groups of people, even identification is more or less accurate, and then it goes down as the number of subjects increase. Again, an important idea here that this is a very separate trait. So this is brain-related, and then we have the stuff that is related to the oculomotor plant. Another important idea here is that what happens to the methods when we are decreasing the sampling frequency of the device. So the device with which we used in the experiments had the sampling frequency of 1,000 hertz. So for example, this one, $100 one, has sampling frequency of just 30 hertz. So how well would it perform? So here we have a receiver operating curve that basically tells us how the performance degrades if we decrease the sampling rate. And what we can see here that there is no decrease in the performance until 250 hertz. But really after 250 hertz, this equal error rate becomes larger and larger. The 30 hertz still allow us to distinguish the person better than random. So there is information, but the performance is much worse. Okay. So we wanted then to work on a method that would allow us to combat the degradation in the sampling frequency. So this method represents the attentional strategy, basically how the brain allocates the attention when it looks at something. And what we are doing can be presented with a another video. So you can see here there are two people that look at the video.
Where does your journey end? You seek that which would bestow upon you the right to rule. The quest to reclaim a homeland and slay a dragon.
Do not think I won't kill you, dwarf.
When did we allow evil to become stronger than us?
It is not our fight.
It is our fight.
It's undoubtedly a trap.
It's interesting because directors of movies work really hard that the people would really concentrate attention on certain points. But we saw that there is similarity in terms of where people are looking, but still there are differences.
How can we make sure that this is not the error in our calculations?
By looking at a lot of data. So this is the idea of the method. So we are basically creating what can be called as signature of your attention. So we have this temporal sliding window that goes through the recording and basically creates what we call fixation density maps. And basically those are imprints of the fixations that we make in a short period of time. And so then for each, our segment is 5 seconds. For each segment, we have a map like that. And you can see the difference between two people. Basically, in the experiment that we had, person looked at the same video with an interval of approximately 20 minutes. And so here you can see this is session 1, and this is session 2 from one person. And you can see that they are more similar than what we can see from another person, for example, from the session 2. And so this is the representation of the similarity matrix that we have.
How similar are two individuals over time? The same individual over time?
Oh, this is a topic of separate research. This is what is called template aging. Again, if I can defer this question to the end, I think that would be good.
So your session 1, session 2, the same content? Or
That's right, exactly the same. Exactly the same.
But will it matter you watch it first time or watch it second time?
Yes, a little bit it matters. So it shows that there is enough similarity between first and second session, and my deferral of the question, what happens if you watch it, third, fourth, and 10th
time?
time?
If I drink a glass of wine before watching it the second time?
Excellent question. Can I also defer it to the end? I'll remember. So that way you will have more information by the end. So hopefully it will allow me to be more effective in the way that I present. So again, we looked at different metrics that would allow us to compare those attentional templates. In our case, Earth movers distance, which is relatively simple, allowed us to get quite well the best performance that we were able to get. We looked at also different fusion mechanics, and likelihood ratio was again the best. So the system was identical to what I was presenting before. So this is exactly the same setup, same 335 subjects, and the stimulus was 1/2 of the official trailer for Hobbit 2. So this is the performance. Again, here we are increasing the number of subjects, and you can see again that for authentication scenario, it's good, right? So, well, again, comparatively good. It's close to this 10% line. And again, it's another trait that we are considering. With identification, not so good, plus decreases with the number of people.
Is it the number of templates you're matching against? Is that when you say?
That's right. So we have the database, right? So the database is basically collected. It is divided in the training testing set and revalidation. I think we have 20 times revalidation, basically randomly splitting the training testing. And so this is the subject pool that we are working with. So this is how the degradation of performance occurs. So this is the performance of CM, previous metrics that are related to the brain, when sampling frequency goes down from 1000 to 30 Hertz. So here you can see that those methods perform for this specific content, and the performance of the method changes depending on what you're working with, whether text, video, and the duration. So here it was at 20% and increased almost to 30%. But the performance of this fixation density maps method that only uses solely fixations was pretty stable even when it went down to 30 Hertz. And we even tested at 15 Hertz. It's comparative, very comparable to what you see here for 30 Hertz. OK, a few words about even another trait. So could you please move your eyes between 1 and 2? So back and forth again and again and again, right? So do you think you're very accurate in terms of how you position your eyes on those points? How many of you think that you are very precise? No? OK, very good. Actually, there is quite a few corrective behaviors. So those are different cases in terms of how our visual system performs. So here I have this simple line, straight line, is basically the position of the stimulus. This is the jumping position of the dot. And this is what is called normal saccade, where we basically match. With the saccade, we match the position of the stimulus quite well within a certain threshold. Then what we can see is undershoot. Basically, the system undershoots the target and doesn't correct. We have simple overshoot, where the system overshoots the target and doesn't correct. We have dynamic overshoot, basically the pullback from the anatomical, from the muscles. We have express saccades, which are saccades that are very closely spaced. Usually for our human visual system to make a new saccade, we need at least 200 milliseconds to program the signal for the extraocular muscle to execute the new saccade. But there is a phenomenon that is called express saccades. Those are saccades with the latencies of less than 150 milliseconds. And some people have them more, some people have them less. There's also corrective undershoot, where we basically undershoot the target and then correct to the target. Corrected overshoot. Overshoot the target, correct. Then we have multiple corrections of different kinds, and even compound saccades that are very weird signal, where you basically go back and forth trying to position to the target. And I'll come back on the question of alcohol with that. OK, so exactly the same setup. And we are looking only at the uniqueness of this corrective behavior. So here you can see that the authentication performance is actually much worse than for the other method. It's not random, but ER is at 30. And the identification is quite bad, approximately 10%. OK, so here I would like to concentrate. This basically concludes the talk with how I can identify a person based on what characteristics. And some of the questions I would defer to the future work, which I'm going to talk about later. And right now I would like to concentrate on spoofing. First, I would like to start with a few ideas how you can basically spoof a system that either use iris or eye movements or both. So if you can believe me, the most successful attack that you can employ to fool an iris recognition system is to capture a person's iris on the camera, which you can do with today's technology at a distance of 12 meters, print this iris pattern and present it to the system, making a little hole for your pupil so you would get a corneal reflection. And a lot of real commercial iris recognition systems would be spoofed by this simple technique. So this is one idea. The second idea is pre-recorded video. So let's say if you have eye tracking based system, what would happen, let's say, if you have a camera and you would pre-record the eye movements and then just give it back to the system. And now I would like to go back on the question in terms of randomness. For oculomotor plane characteristics, because the anatomy of the eye stays the same, no matter what saccades you are executing, it's still a pretty reliable method to authenticate a person because physiology of the eye doesn't change. Brain behavior is a more difficult thing, but with oculomotor plane characteristics, you can identify a person even if each time you present a new random stimulus. And that way, why intuitively pre-recorded attack would not be effective. The third type of the attack is the case where the intruder imprints things on the contact lens, the video that you saw at the very beginning. We have not published anything on this topic. Intuitively, again, the system would fall back on the not iris recognition, but on eye movement biometrics. The fourth case is the most interesting theoretically. So the case of mechanical replicas. Who watched the movie Terminator? Quite a lot, right? Remember how they try to identify who is Terminator and who is not? Dogs, that's right. Actually, eye movement biometrics is the most effective way of identifying who is a Terminator. Well, you can tell me, of course, that I'm crazy, but yeah, probably the smell. So here is the attempt of scientific group from Germany to get the mechanical replication of the eye. As you can see here, we have €1, so the system is relatively small. You can, of course, see that it makes some non-human-like movements, and especially the speed at which it rotates is not exactly the same as for the natural system, but at least, I mean, we have a concept where certain things are possible. Mathematically, we analyzed how difficult it would be to spoof the system that uses eye movement biometrics with replications by mechanical replicas. And here we basically mathematically implemented the mathematical models of the eye that exist, and then based on this signal, try to spoof, at least theoretically, the system that we have. So for example, this is one of the first representations of oculomotor plane, Westheimer's second order model. In those orders, for example, second order means that the differential equation that describes the dynamics of the system, characteristics differential equation, has two orders. So it has different disadvantages in terms of it even doesn't generate realistic velocity profile. So it's very easy to detect even without looking at anything sophisticated. So the second model that we looked was a Robinson. It was a more complex model that provided more accurate velocity profiles, but still were not realistic. And the third model was the one that the model that was created by me when I was doing the dissertation and refined by my students. So this is the model that I presented to you. And we actually looked at even one more model, Enderless model. And this is how we try to generate the spoof signal. So remember that the live system has a lot of corrective behavior. So we try to do the same thing by injecting this instability into the system so it would make those overshoots, undershoots, and also inject jitter during fixation. So we try to do whatever we could to make it as human as possible. And so this is how the system was spoofed, basically to this mechanism of identifying a person based on oculomotor plane characteristics. We either fed the live signal or the signal generated by those models. We have extracted the biometric template, and we have analyzed the numbers in those templates. And here's an important idea, is that human people are very, very variable. So they have a lot of variability embedded in them. And that's why we are so complex, have problems, and many other things. But an important mention here that for mechanical system, it's extremely difficult to replicate same type of variability. And if you want to do it in a mechanical system, it much more increases the complexity of your system. So by looking at actually quite simple statistical methods, such as PCA, and looking at the covariance matrices that are generated by the data, we were able to find out whether the data came from the mechanical system or from the live system quite easily. So we used basically the same setup, and the system was, the person was making horizontal saccades, or the mechanical replica was doing the horizontal saccades. There are two important scenarios. First scenario, where the intruder generated the mechanical system just based on the averages that are published in the literature, those averages from those three people. And the scenario B, that is feared by many corporations, is that where your passwords, or in this case biometric data, is fully compromised by the intruder, and they have access, direct access, to your authentic biometric template. And so they use this biometric template to create a perfect mechanical replica. So in those systems, we found out, so the performance metric here is correct recognition rate, and 1A was the most simple system. So you can see most simple system that spoofed the biometric system. So correct recognition rate was the highest. And for the B, where everything was compromised, still the detection rate was high. And we also have unpublished results where, by additional analysis, we can get those numbers close to 99. So it's very reliable in a way how you can detect this mechanical replica. OK, so the conclusion here is that we have extremely high detection rates for the mechanical replicas of the eye. And this is a very important property of the biometric system. We also have work that allows us to defend against printout attack, but again, it's unpublished, so I'm not going to talk about it here. So my overall vision in terms of how the system works, and I call it ocular biometrics approach, is that on the iris recognition device, and again, iris recognition device is basically image sensor and some infrared lights, we are able to collect iris information plus information about the oculomotor plant and the brain. And that way, the system becomes very, very accurate and very secure. And so funding for this was provided by NSF and NIST. And if you Google, for example, for eye movement biometrics or passwords, you will see a lot of articles about the work that we have done. OK, so future thoughts. So probably you all know this. This is Google Glass. So the idea is how we can employ or how we can authenticate effectively using Google Glass, right? Right now, basically, you need to swipe. It's very cumbersome to basically either protect your device or do something that is not really natural. So the idea is, what if it would be possible to identify a person basically put the device on and then read the line of text, and then the person automatically detects that this is you. And then if somebody else puts the glasses on, it would immediately detect that this is not you. Well, the challenge of the Google Glass is that the amount of power that is available to device is quite limited. They actually have a camera that is facing the eye, but it's very small, just 1 pixel. So the question is, can you design a device that would allow you to do eye tracking either with this 1 pixel camera or with a little bit bigger one? And this is where there is an advantage of eye movement biometrics over iris. Iris, to work correctly, needs really high resolution camera to get the eye image and then do some processing on this image. For eye movement-based biometrics, it can work even on images that are much smaller. But again, this is a future work and something that we are interested in working on. Other applications of the technology, and after this, I will come back to your question about alcohol. So right now, there is a big problem, for example, in professional sports in terms of detecting traumatic brain injuries. So what we found out, because we are extracting so many metrics from eye movements, more than 50 at the moment, we are actually able to identify quite reliably in terms of who has mild traumatic brain injury or who is not. We have a very limited sample, and we would like to grow it to more people, but for the very limited database that we have, we identify people with 100% accuracy, and we published this paper at CAI that was presented this year. In addition, with eye movements, because really you are getting the information about the brain behavior and about oculomotor plane behavior, you can tell quite a lot of things. And yes, you can tell whether the subject is fatigued. For example, the corrective behavior increases dramatically. You can tell if the person is drowning. They even cannot follow the single dot on the screen. So if you have a variable computing device that is able to do eye tracking, not only you can basically interact with this device by using eye movements, but you also can be authenticated, and your psychological or physiological state can be detected. But in terms of what we can do, only traumatic brain injuries is a published work. And then, of course, the questions from you can be, so is the performance affected by the alcohol? So basically, right now, we don't know how the template changes. But we really can see that there is a sense in doing this analysis in terms of if the person has traumatic brain injury, in terms of personalized analysis. So if we have a biometric template when the person is healthy, and when the person has a certain pathology, for example, acquired as a result of the heat, we would be able to detect this pathology much more accurately than just based on some averages that are recommended by the research literature. That's right. That's right. So there is a research, and so I can now come back to the template aging question. Yes. So everything in us ages, and so the performance of the muscles changes, of course. So the muscles become less elastic, and so they change their properties. Yes?
Yeah, the reason I mentioned the glass of wine is that it's an extreme example. But basically, the motor skills are affected by a number of things. Like if you are angry, for example,
yes,
you have a higher level of hormones in your blood, and that changes the way your muscle reacts.
Right, exactly.
So on this repetition thing, I mean, the classical way of sampling is voice recognition, that you try to recognize your voice, and then you have to call it, and it doesn't work anymore.
Right, exactly.
And so do we have similar problems?
Yes, I think we do have similar problems. So unfortunately, the resources of my lab are limited, and so we are able to say what we are able to say based from our experiments. So we have not conducted extensive studies either when people are drunk or concussed. We have a very limited database. But when we have acquired those people, so we are writing, whether they drank within a certain period of time, how many hours they slept, how much coffee they drank, and so much like information like this. We just did not have time to analyze. Actually, the lines that I'm presenting, the performance slides, they're not even published. So this is for you guys. So, yes.
I agree with Christian that there are lots of interesting individual differences that could be familiar. Things ranging from fatigue and anxiety, and whether you've had a fine glass of wine or familiarity with the task. Do you have any way of characterizing what those are? I mean, they're probably not random differences, right? And so it would be interesting to. That's why I asked about the differences within an individual.
Mm-hmm. Yes, I don't think they're random. This is sort of research in terms of we have an application, biometrics. Can we make eye movement work in biometrics? For example, psychologists take a fundamental approach where they break the performance of people into very controlled experiments, and they publish meticulous journal papers on each small change in a person's state. I don't have the luxury. I would love to do it in the same way, but I don't have a luxury. So I can only report numbers from very large recording of people. And we also have longitudinal recordings, basically recordings over the course of 8 months, but we just did not analyze all of the data. The only thing that I can tell that there is definitely template aging. So those ER would increase, let's say, if the person was recorded again in the period of 20 minutes, or she or he came back after a period of 2 weeks. Even 2 weeks, we see the differences that affect ER. So definitely there is a notion. For example, right now there is a fight in biometric community if there is a aging in, for example, in irises. And so there are different arguments on that. So here I can definitely say there is no need for the argument. There is a template aging problem. So which should be researched more. Yes?
Going back to the individual differences briefly, there's some work from a few years ago that shows that for repeat scan pads,
yes,
that people begin to become more efficient and they effectively chunk those scan pads at some level. So I wonder, one, do you have a signal there at the rate of learning? Is that another signal you can see a person converges through time? And the other is, does that raise any challenges for you in terms of the kind of fixation points or the kind of targets that you present to a person? So if you present random ones, will a different kind of efficiency emerge in how they scan them? So,
right. So there is a literature that that specifically talks about scan paths. What I can tell that biometric performance would be different for different stimulus. There is a statistically significant difference in terms of how much we can extract. For example, for the movie that you saw, the amplitudes of the saccades and distributions of those saccades is different than, let's say, for completely random stuff. So the amount of oculomotor behavior that we can extract would be less, just because we execute less saccades, because subject can, tired and he doesn't want to look at anywhere, just, follows. Or even with text. So one of the stimulus that we presented was text. Some people meticulously read the text, others just, give me the $20, right? So like that. So there are definitely a lot of interesting information that can be extracted, and unfortunately the only thing that I can say that we have not analyzed it. So this is actually not the end of my talk. I think I have time till 1. Because I have human-computer interaction component. So eye movement interaction.
Is there any kind of a upper limit which you guys have analyzed in terms of failure rates? Like, for example, we know for face recognition, it's around 1 in 10,000, fingerprints 1 in 100,000.
Yeah, so those, so remember the ER is where the false acceptance rate equals false rejection rate. We can change that, so we can make it more toward false acceptance, less false acceptance, but then false rejection would be much higher.
Yes, but what I meant was that even exactly for that ER, right, there is you can see kind of what kind of a degree of freedom you have, and that's exactly what you were talking a few minutes back, where you said there is a limit to the variability in the saccades and positions where a user will point at. So is there basically a limit? Like, for example, we know, again, coming back to the example of face which is around 20, fingerprint around 30, eyes around 180. Where is this limit? Where does it fit in this bin?
So I would wish that I would answer it beautifully like John Dugman did for the iris, where he basically mathematically said that, our irises are so highly unique that, those distributions between the imposters and authentic users are really quite separable for quite a lot of people. What I could have done theoretically, of course, inject some differentiate oculomotor plant characteristics and try to analyze it theoretically. We have not done that work, but definitely there is a lot of similarity. It would be actually quite surprising to me if it would be really fundamentally different on the level of muscle design. Right? For example, for iris, the pattern is formed when we are still in the womb of our mothers. And so it's basically completely random, where here it has a certain purpose of guiding the eye. So the mechanisms are actually quite similar for each person. And if you look at the psychological work, most scientists study how people are the same and trying to average the performance and see how similar we are in our behavior. And only biometrics study how different we are. But the majority of the biometrics branches study static traits, such as face or iris or fingerprint. We can only name a few. The one is more or less established as gait, and there are more, I guess, exotic ones, such as heart rate or EEG, and they also have advantages, disadvantages.
When we analyze faces, what we see is that the difference between faces increase a lot with age. Like basically all babies look the same. And do you have something similar there?
Yeah, so there is published psychological research that basically states the maximum velocity during saccade changes with age. So it immediately, so those few fundamental metrics that we are employing would be affected by aging. But for example, if you would say how it would affect the movie, looking at the movie, we don't know. Like for example, how the distribution of fixations, because remember there are two questions, how we move between points and where. So how the age affects where our eyes are pointed, I don't know. And I don't know the literature that would investigate that point. Okay, so a few things that might be also interesting to you about the design of eye-gaze interfaces. So this is the example where something that we have designed in the lab. And this is basically a photo viewer with the idea that the person would be able to select, let's say, different images by looking at folders and then selecting a specific image, and then this image would be presenting to the person. And right now, eye tracking and human-computer interaction is popular mostly for the disabled users. So you can interact much more fluidly, for example, than with EEG, things like this. I think actually Windows 8 is, in my opinion, quite well designed to work with eye gaze because there are tiles and you can change the separation between tiles. And those are the numbers from my lab in terms of when we experimented, we found sort of optimal numbers. So for example, for the layout for well-performing eye gaze devices, for example, for something like this, should be greater than 0.5 degrees of the visual angle. Once again, it's the quarter of the thumb, not less than that, otherwise there would be problems. And individual component size should be greater than 2 degrees of the visual angle. And those are the recommendations that we have. And sort of for the conclusion of the talk, I wanted to present something that I hope to be thought-provocative. So here is an image video from a game. And the goal that I have for you guys, so the task, trying to understand what is the goal of the main character in this movie. So what do you think, guys, is the goal of that guy?
He's a healer in World of Warcraft?
No, actually, he's doing damage. So his idea, his goal is to do as much damage as possible before he dies. So with that goal in mind, and actually this branch of research, I was and still am a big fan of Warcraft. And so it was inspired by this game. So the idea here is to select a target as soon as possible, to create a target. If you are able to select a target as soon as possible, then you would be able to do more to that target. And in this case, it's damage. Okay, so let's look at how basic mouse-based selection work. So what happens, the brain sees an interesting target in the periphery, and then basically it looks at that target. And then the hand with all the muscles and bones moves the cursor to the target, and then there is a click. Well, with a conventional eye-based selection, what we can do? Again, brain sees the target, programs the eye to go to the target, and basically eye dwells on the target, and then the target is clicked. And so then we basically reduce the amount of time by the time that we need to move the mouse. And so the idea is, can we actually do better than this? And sort of, can we click instantaneously? So just, program the movement to the target and then click. So this is the idea. And first of all, so this is how the conventional method works. So this is the time where the brain is programming the signal for the eye to go to the target. We have a saccade here, and then with the dwell time, we select the target. And what I want to do is that immediately after the signal is computed, I would like to select my target here. The eye even did not land on the target yet. Well, it makes sense to find out, how much time it would save if such method would be implemented. And here is basically my simple theoretical analysis where I have target acquisition time, then saccade duration, then the dwell time. And in the method that relies on instantaneous saccade selection, there would be target acquisition time. And I start moving, and then I select. And k basically how many samples I need from the eye tracker to determine where the saccade is going to land. And then roughly speaking, considering the size of regular computer screen, my speed up would be 35 to 45%. So I need two parts. First part that would detect the onset of a saccade, the start of the saccade in real time, and then predict the amplitude. So the question is whether it's possible theoretically and whether it's possible practically. So in theoretical evaluation, because now I have this model of oculomotor plant, again, that I presented to you, I can analyze this signal. And so what I do here, I employ the Kalman filter to process the signal and use the chi-square test to also analyze the signal. And what I can see in the chi-square test part of the signal, I see those two distinct peaks. And the time of the occurrence of the first peak doesn't exceed 14 milliseconds. So if I can connect the properties of the saccade to the properties of this peak, I would be able to predict where its saccade is going to land and click the target in 14 milliseconds. And so the first question, is the size of this peak correlated to how far I'm going to go with the eye with the saccade?
Clarify again what that peak is. Is it the detection of the saccade?
So,
or
okay.
The location, the destination of the saccade?
So basically, because I have a model, I can simulate as many saccades as I want. So what I'm doing is basically simulating the trajectory of a saccade by a model. And on top, I'm putting two-state linear Kalman filter. From the Kalman filter, I'm getting the prediction in terms of what my velocity is. I'm analyzing this velocity by chi-square test and running this temporal window, so which gives me this precise signature in terms of how the signal is going to look like. And then I'm connecting the properties of the predicted saccade to the properties of that peak. Okay, so and what I can see here is that the saccade amplitude and the value of the peak are very, very well correlated. So I can predict where it's going to go quite accurately, at least theoretically. So that was practical evaluation. In the practical evaluation, I'm basically doing a simple task of selecting the target, and target is moving back and forth only horizontally and randomly, because in the two-dimensional movements are actually much more complex than horizontal movements. Okay, and so basically it's a Fitts law test, and the numbers that I'm presenting here is that it was much faster to select a target using instantaneous saccade. So I have 57% in reduction of completion time. And you saw in theoretical analysis, this number was actually much smaller. And I think the difference because we misevaluated the amount of latency or target acquisition time that usually occurs in the human visual system. And in terms of the throughput calculated as a result of the Fitts law task, we see that there is 48% increase in terms of throughput. Well, what is the disadvantage of this method? Like any eye gaze-based method, it has an inherent problem, of course, the Midas touch problem. So if you employ this, your application should not suffer from Midas touch problem. The question is it possible to create an application like this? And again, World of Warcraft is a much example that is geared toward this, where if you erroneously select a friendly target, nothing bad happens. So basically, you can only do damage to unfriendly targets. So in that case, it's a problem of a designer how I can create the interface where erroneous selection doesn't cause any problems. But again, it is an interesting problem because now I can do things much, much faster than before. So we have created also a simple computer game that simulated a World of Warcraft environment. And what it is, basically we have balloons. We have red and blue balloons. So blue ones are friendly, and red ones you should pop with your eyes. And this is the method of doing it by dwell time. And you can see that it's very hard for the person to dwell on the target and get selected. And so tasks take quite a substantial amount of time. And for instantaneous Saccade selection, it's much, much quicker. So you can see here that the person is able to pop those red balloons much faster than before. And actually, when we do the introduction of computer science to kids who are interested in STEM education, they love this game, and so all they want to be computer scientists and design games that are moved by the eyes. Okay, so in terms of future work, it is my personal goal sort of to make eye tracking part of existing iris recognition devices, and I believe that it can be done with a software upgrade to increase the security of those systems. Also, to create methods for user authentication for on-the-wearable devices like Google Glass, and also employ this technology to test for pathologies, psychological or physical state. And I would like to acknowledge the funding that I have. Those are the sources. Thank you so much, guys, for your attention.
Thank you.
Yes.
Yeah, so I think it's going back to the previous question of spoofing.
Okay.
So there is this, I'll probably give an analogy to speaker recognition problems, right? Where you ask the user to speak for a certain time, and then they have these graphs where they say the longer you ask, the more features you can actually collect, and the stronger classifier becomes. So in terms of any biometric, the bigger factor from a human usability perspective is the snappiness, right? I mean,
how fast?
Cruise,
yes, that's right.
That's right. Saccade was just looking at something and he was recognized, right? When you start putting in features like eye movements and so on, the bigger question, of course, is that how long the user has to do all these movements before you actually think he's not spoofing.
Okay, so we start to be non-random, sort of from 10 saccades. So 10 saccades, and then for 40 saccades, we have quite good biometric performance. After 40 saccades, let's say after 40 saccades, sometimes we see issues such as equipment slippage, and this is, for example, for the desk-mounted system, or the person gets fatigued. So the data becomes more noisy. However, statistical methods can remove part of this noise or cope with this noise. And so the final research conclusion was, again, the more data we have, even if it's noisy, the higher is the accuracy.
But your golden number was around 40, is that what you're saying?
40, right. So where we have the highest quality of our signal. So I think it's a good balance between accuracy and the amount of data that should be collected for the first decision to say who is who.
How much time was it approximately taking?
So in terms of physiological limitations, how quickly we can pump out those saccades, right? So maximum, you can make approximately 4 or 5 saccades per second.
Oh, okay. So
your maximum count. So at least, so the more time, the more comfortable you are doing it, right? So 4 seconds, so whatever. Yes, that's right. 8 seconds is the answer.
No more questions? Okay.
Okay, great. Thank you very much.